Okay, so yesterday I gave a general motivation and went into this topic of high-dimensional parameterized PDEs. I show one very simple model and gave you the main results on polynomial approximation based on sparsity concepts. And then we saw that it was also possible to attack other models and get quite similar results somehow with different techniques. But in the end, the message is the same. You can benefit of this anisotropy underlying the phenomenon, the fact that certain variables have less sensitivity than others, to derive approximation results that are robust with respect to the number of variables. Okay, and now I want to go to numerics, and we are going, in a way, as I said, to land. It will be less technical, and it will apply also to other problems. So, yeah, as I was saying, for these particular problems, we are facing two difficulties when we want to execute these approximations, compute them. We have to compute this polynomial space. We have to understand which are these index sets we want to use, and in principle, we should compute all the coefficients in this expansion and look at which are the largest one, but we cannot obviously do that. So we need strategy to identify them. And secondly, once we have identified them, we need strategy to compute these polynomials. We cannot compute the exact projection. And this is where least square will be an option. Okay? So about the first problem, let me say that there are essentially two approaches. One is what I would qualify as a non-adaptive approach, but still trying to benefit from the analysis that I have done. So in this analysis, if you remember, to prove these main results, we have given some a priori estimates on these coefficients. If you remember, we had a complicated, well, an estimate with this omega to the minus nu, and we could play with that. And these estimates are computable. These are not exactly computable, but these estimates are explicitly given to us, and we can use them to decide which are the index that we are going to pick. We are going to pick not the n largest of these, but the n largest estimates. This is what we have. Okay, so that's a rather a good pick. More clever than just picking simply saying I'm going to take polynomials of degree 2 in every variable. I don't want to do that. Okay, we really want to exploit the anisotropic structure. Or something more risky but more interesting is to proceed in an adaptive way. So in an adaptive method, you start from a very coarse set, very coarse space, let's say constant. You just have the index 0 degree in every variable, and you first compute something. You compute a solution, and based on what you have computed, you try to enrich your space based on some a posteriori criterion. So what this criterion is, I don't go into detail, but it has to take into account what you have, the information you have gained in the computation. So, for example, you could think that you would have already this set, and now you want to grow it. So let's explore its neighbors, and let's try to have all kinds of a number of candidates, and you would like to decide, am I going to add this one or this one or this one? Okay? Let's say my a posteriori analysis tell me this is what I want to enrich. and then I proceed this way. Okay? Question is, how do you exactly identify this? That you have to, you need some criteria. I'm not going to go too much into that. There is something interesting with adaptive algorithms for this structure. In fact, my picture is already hinting something. The idea of this front that moves, and that I'm not going to pick one coefficient out of the blue, completely isolated from the rest. Okay? So, in fact, I am suggesting that we are going to use index sets that have a certain structure that we call downward close. Namely, that whenever an index has been chosen, all the lower degree are in the set. Okay? So we call that downward close or lower sets. Okay? Now, of course, if you think of these sets of the largest coefficients, they could be not downward closed. And I want to avoid that, okay, for practical computational reason. But if you inspect the result that I gave and all these techniques, you can actually show that the same convergence rate will be maintained while imposing downward closed structure. So there is no cost. I mean, there is no, it doesn't hurt you, in theory at least, to impose this structure. Actually, this structure makes sense if you remember, for example, the type of recursion formula I have for the coefficients. I think I gave this formula somewhere. Yeah, here. For example, if you think of the Taylor coefficient, by differentiating the variational formulation a number of times, you get this formula that tells you that the coefficient T nu is given to you by a boundary value problem, where on the right side you have the coefficient T nu for lower degree. Okay? So it means that if you know these guys, you can compute this guy. You can recurse this way. So it perfectly makes sense to impose this structure, because in that case, if you want to compute recursively the Taylor coefficients, you would need that, because to compute this one, you would need this one and this one, right, according to this formula. Okay. So you see, once we have chosen a certain downward closed set, we consider this, this polynomial space. And you see that because the downward closeness, this property also implies that you can define this space in different ways which are equivalent. You can define them as spanned by the monomial, or spanned by the Legendre polynomial, or spanned by the Hermite polynomial. Why? Because this is a triangular change of basis, right? You can re-express the L nu, the Legendre polynomial, as a combination of the monomial of lower degree. And similarly, you can represent the monomial of a certain degree as a combination of Legendre polynomial of lower degree, right? So this is a very stable notion. And again, if we work not with quantities of interest, but really if we want to capture the solution, we are thinking of v-valued polynomials, so the coefficients are v functions. Okay? And once we have selected this lambda n, we search for some computable approximation of u. And this is what I want to discuss now, and I'm interested in non-intrusive strategy. So we're going to base our method on snapshots. Okay? So note that I put the I on the exponent on the top, not to confuse with the component of yi. For each I, yi is a vector with d coordinates, okay? So, as I said, the first idea could be, one idea would be pseudo-spectral method, which is to say we compute this coefficient by some kind of quadrature. There's something even simpler we could think, which is interpolation. Maybe that's the first thing you think when you want to build a polynomial from snapshots. You think of interpolating these values. So interpolation means that we're going to use a number of snapshots, which is exactly the same as the dimension of this space n, right? In 1D, if we want to reconstruct a polynomial of degree n, we need n plus 1 points, okay? Distinct points. Okay, that would be the simplest idea. I will explain. Maybe I will say a few words about it and say why this is not such a simple thing to do. Okay, least square is what I'm going to develop. There could be some weights as we have seen, so we try to minimize, and here we typically going to use a number of snapshots which is now larger. So this is in a way overdetermined. But we could go actually the other way around. We could say, okay, we're going to have less snapshots than the potential degree, okay? And in that case, this is underdetermined. We have infinitely many solutions, so we need to penalize. We need to select one. One typical way is to say we're going to add some penalty term. And for example, an interesting option is to take some L1 penalty. That would be the approach in compressed sensing. So I'm not crazy about compressed sensing approach for this particular problem, because you live in an extremely high dimensional environment. And so the idea of searching for the minimal L1 solution in a very, very high environment, even if in the end you end up with a very small support, I think becomes quite costly in this particular context. So I'm not going to talk about this. I'm mostly going to talk about this and a little bit on pseudospectrum. But maybe I will say a word of interpolation. This is not in my slides. So, you know, as I said, non-intrusive methods are interesting. They're applicable to broad range of model. You don't actually, all you need is a solver. And we have all kind of numerical evidence that says that it works well, also with adaptive approach, but we don't have any theoretical guarantee for adaptive approach. Right. So what's going to be important, as I think I mentioned this in the beginning of my lecture yesterday, we're going to enrich this space. And what we would like is that every time we enrich, we can recycle the snapshot that we have used before, the evaluation, the queries that we've made. And we would like that these methods are stable, accurate. In the case of the interpolation, we know that stability is related to what's called the Lebesgue constant, so we would like to have a good control on that. And the main issue is going to be how to best choose this point. So I will focus on least square, because we have, this is in a way the methods where I have invested some activity, because I think there are interesting stability and optimality results using some random sampling. But before, maybe I want to say a word about interpolation, which is the simplest idea you could think of, just to explain you why there is a difficulty. Okay, so what is interpolation? Right, this is you have a space Vn where you want to find your function. You have y1, yn, some points, and your interpolant, okay, is going to be given to you by the function un in Vn. So let's say that we have a function u, which is our target function, u to be approximated. And we're going to pick the element in Vn which agrees with u at these points, right? Such that u of x of yi agrees with un. Okay? So you have n unknown because it's a space of dimension n. And n equation. All right? Suppose you have one solution. You would like to know how accurate this is. Okay? And this is going to be described by the Lebesgue constant. So what is the Lebesgue constant? So un, you see that this un is going to depend linearly on u, actually, because you can write un of y as a sum for I equal 1 up to n of u of yi times some functions which are the Lagrange functions, Li of y. And what are these Li of y? Li of y are the function in Vn such that Li of yj is 0 if I is different from j, and 1 if I equal j, right? It's delta or I minus j. Okay? That's, so you know you can think of this as it's an operator En applied to u. Huh? And what is the Lebesgue constant? Lambda n, little lambda n. It is a norm of this operator from L infinity to L infinity. Here we're going to measure error in L infinity. So it is the max of In of u in the L infinity norm over u in the L infinity norm, right? And it's also something you can compute from this Lagrange function. It's the maximum value over y of the sum of the Li of y, absolute value. Very easy to verify this. Why is this object the key? Why is this the important quantity? Simply because let's try to look at u minus un. In L infinity, and now you take any function from this space Vn, take any v in Vn, or any little Vn in Vn, and insert it, use triangle inequality. You get that this is less than u minus Vn. Okay. Plus Vn minus un. But what is Vn minus un? You can also say that un is inu, and Vn is in Vn, because the interpolant reproduce functions that are in Vn, right? This is still the L infinity norm. Huh? It's always the L infinity norm. Okay? So you see that now using this bound, this L infinity bound, I get that this is less than 1 plus lambda n times u minus Vn, but Vn is whatever I want in Vn. So I can put that this is less than 1 plus lambda n times the infimum of u minus Vn for any Vn in Vn. So this is what I was calling instance optimality. You want to say that your approximation error is essentially the best, but here there is a price to pay. You have the Lebesgue constant. Okay, it's a very trivial thing. Now how large can this Lebesgue constant be? So just to explain you that there is a difficulty here, think, for example, of you see, you would like that this lambda n, this is the error, and this is going to decrease, but you would like to have that this lambda n stays in control as n gets large. Okay? So, about the Lebesgue constant, think, for example, of a very simple situation. Take Vn to be polynomials of degree n, or polynomials of degree n minus 1 if you want to have a space of dimension n. Okay, let's say Pn in dimension 1. So you work in L infinity of some interval of minus 1, 1. And of course, in order to understand what is the value of the Lebesgue constant, I need to specify where I put my interpolation point. Okay? So the first idea that could come to your mind is to say we're going to interpolate at equispace point. Y1, Yn, all right? Is this a good idea? I think some of you who have seen polynomial basic thing, yeah, you know it's not a good idea to do that. Because if you do that, you know that lambda n is going to behave like essentially 2 to the power n. Okay? Terrible. So how should you actually sample in that case? I think you must know the answer. I mean, what are the good interpolation points in 1D? Gauss points, Chebyshev points. So what is the recipe? The recipe is essentially to take a half circle and to take a uniform sampling here and project. And you get what's sometimes called the Gauss point or the Clem-Shaw-Curtis point, the Gauss-Lobato point. Okay, and these are good points. These are good points because lambda n essentially behave like log of n. Okay? But now I told you that I would like to have progressivity. I would like that every time I go from n to n plus 1, I want only to add one new point. Is this what's going to happen here if I go from n to n plus 1? You see, if I have n equispace point here and I go to n plus 1, everything gets scrambled. Okay? So now I'm asking to you this very simple question. Suppose I would like that my space yn, my point yn are picked from an infinite sequence. I would like that I have a unique sequence, yj, j bigger than 1, and to say that my point are going to be the section, the first section of this sequence. So I impose progressivity, you see? How can I do that in order to be as good as I can, okay? So there are recipes to do that, but here is the bad news, is using this recipe, the best I know to my knowledge, is going to be that lambda n behaves like n squared. Okay, this is actually a result proved by one of my students, Abdelash Kifa. And that's his name, he's from Morocco. And it's, you know, it's a bit painful. You would like to say it should be possible to keep this optimality and be progressive. But there is a real trick here, okay?
This is 1D or
1D, 1D. So I'm saying, even in the simplest case,
because it's not a hierarchy.
yeah, it's not hierarchical. So if you think of these points, for example, they are nested if you double the number of points, right? But the question is, so if you just look at powers 2 to the n, okay, then this is going to be okay, but how do you fill the gap in between? That's a real question. If you do it in a very stupid manner by inserting from left to right or from right to left, the intermediate value of the Lebesgue constant is going to be horrible. It's going to be essentially like that. Okay? So this is a very simple problem. It's 1D. But already here I don't have an answer. Now, you see, I wanted to treat a problem in full generality. I wanted to work with any space Vn and ask you, is there a good way to control the Lebesgue constant to find good points? And we already see that in 1D for this, there is a problem if you want to be progressive. Let me say something about the general problem. If you have a full space Vn, there is a very simple way to design points which will have a reasonable Lebesgue constant. You take a basis from Vn, your favorite basis, L1, you take a basis L1 up to Ln, a basis of this guy. Now they are not necessarily polynomial anymore. And you form the collocation matrix Li of xj of, right? For any n-uplet of points. And you look at the determinant of this matrix. And now you take this determinant to the maximum. You maximize over the points x1, xn. Okay, so you pick those points so to maximize, and that gives you your interpolation point y1, yn. Okay, now if you do that, this is a little exercise for you. You can prove that the Lagrange functions that I gave you are bounded by 1 individually, so the Lebesgue constant in that case is always at most linear. Okay? Not difficult to prove, and this is an instance of what's called Auerbach lemma. There's a more general situation, actually, and this is a particular case. Okay. So if you think, for example, of the case of polynomials, this determinant becomes a Vandermonde determinant, and it means that you are finding the point that maximize the product between the distance. These are the Fekete points. But of course, this is a crazy problem. You are potentially in high dimension. You have n points you want to maximize over n points which live in high dimension. It's a completely non-convex problem. It's absolutely crazy. You cannot do that in practice. And in addition, it is not sequential. It is not progressive. You could think of a progressive version where you have these points and you add a new point every time you enrich, so to maximize the determinant. But then again, I'm lost. I don't have any control on the Lebesgue constant. So that's just to tell you that interpolation, although it looks very appealing like that, simple, it's full of difficulties, especially in high dimension. and if you want progressivity, and if you have space which are not very standard space, then this is there are difficult problems. So this is why I'm going to switch. What I will show you is that if I go to least square instead, I'm going to fix things. I'm going to retrieve instance optimality, but there will be a price to pay. Things will be not measured in L infinity, but in L2, and the results are going to be of probabilistic nature. Okay, so we have to accept this. These are some reference for what I'm going to discuss. This whole story started with Mark Davenport and Danny Leviathan, and we exploited that, and then we became aware that the key was how we sample and how we weight the least square method, and this is what I will describe. These are work by with Giovanni Migliorati, and in the end we are able to do that in a sequential manner. And I want to say this is very close to work that Ali Reza Doustan from Colorado, I think, did. So, okay, these are the same slides that in the beginning, so it's just a reminder. This is a general context. We have a prior, we have an n-dimensional space that could be a polynomial space, but now that could be anything else. Okay, all options are on our desk. I'm only assuming that this space is well adapted to have a good approximation error, and the error is measured in L2, always with respect to a certain probability measure. So think that, for example, you are on a bounded domain, you could think of the uniform measure normalized by the volume of the domain. Okay? That will be my game. As we saw in the case of parametric PDEs, one typical choice is to use sparse polynomial space, but you could think of something else. And again, I'm after this kind of result, instance optimality or rate optimality, and I'm going to use more than n samples for that, not like interpolation, but I would like ideally not to use too much. Okay? If I could use n, 2n, or n up to log factor, then I would be satisfied. And I want this progressivity. So you remember the idea. We start from the exact projection. Here, L1, Ln is an orthonormal basis of Vn. And since it's out of reach, since all we have are these samples, we are going to replace the integral by this discrete sum, and W is a weight function. Now we'll tell exactly what I want to do. Okay. And this drives me to this method, and I'm mostly going to focus on the least square method, but the pseudo-spectral method I will say a word. All right, so I intend to use random sampling because they're going to give me interesting results. Actually, when I'm in very high dimension, there is not a clear way of putting my points. You cannot usually use in high dimension, you cannot just put things on a grid because it will be much too costly. You cannot put 2 points per dimension, for example, in dimension 100. So we're going to sample, but we are going to sample according to a certain measure, which in general will differ from the measure rho that is associated to the error norm. Okay? So rho is fixed by us. I mean, rho is what we want to use to measure the error. Rho is where we have it's associated to this L2 norm. But now we have the choice on how to sample, and we are going to use the sampling measure of our choice. But we need to compensate for this by using a weight that is related to this sampling measure by this relation. So W multiplying by d sigma is 0. Okay, why? This is quite natural if you think about it. You see, because we are replacing integrals by weighted sums, okay? And you see that when you have this thing, when you have this relation, then this integral can be written this way. And so this weighted sum becomes an unbiased estimator for this integral. You see? Because you can think of if here now, if y is distributed, if the yj are distributed according to this random, to this probability distribution, this is just an empirical average for this expectation. Is it clear? Okay, so let's keep in mind this. Okay, of course, the simplest choice, let's see. Yeah. So we're going to get two resulting approximations, least square or pseudospectral, but now they are random objects, right? Because these guys are random, okay? So if we want to compare UN with U and say is it close to the best approximation, we can only do it in a probabilistic sense. U minus U. This will be a probabilistic object. So we're going to do this in expectation. All right? So of course there would be a very obvious choice, which would be to say, okay, let's not do something so complicated. Let's take W equal 1, and let's sample according to 0. So for example, if we have a Gaussian measure, let's sample according to the Gaussian measure and put weight equal 1. And it turns out that it's a very bad idea. As I will explain in that case, for example, it will lead to very suboptimal results. So optimality will be ensured by a very fine tuning of these objects. That's the idea. That will come. Okay, so why people like least square? Because it's extremely simple to implement. Let me remain. You are minimizing something. It's a projection method, right? So everything can be solved by introducing a basis, not necessarily an orthonormal basis, and you search for the least square solution in this basis. So you search for this coefficient vector, and this coefficient vector is just a solution to a linear system, where G is essentially the Gramian matrix, but where you have replaced the integrals of LK, LJ by this discrete counterpart. Okay? These are the normal equations, and where AK is again an inner product. So this is just like the equation of the projection, except that you project with respect to this discretized L2 norm now. Of course, the solution always exists. It could be non-unique. It's unique if this G is invertible. So again, remember that these yi are going to be random, so G is going to be itself a random matrix. And UN least square is a random function. Note that if we pick for this basis an orthonormal basis of Vn for L2 of y rho, for example, think of polynomials and the uniform measure, let's say we pick the Legendre polynomials. Then you see that this random matrix has an interesting property. Its expectation, the entries of its expectation are given by the inner product integral of Lj, Lk, d rho. And this is the identity, right? This is 1 if j equal k, 0 over y. So it means that this random matrix concentrates around the identity. Okay? So that means that it's likely to be invertible. There could be some probability that it's not invertible or that it's very badly conditioned, and this is what we are going to look at next. Okay, so now I will explain how we analyze instance optimality for least square approximation. And let's start by observing that this approximation is the orthogonal projection onto Vn, but where you have replaced the L2 norm by this discrete norm. Okay, it's like because you cannot compute the projection in the true L2 norm. Okay, so the question will be actually to understand what's going on. We're going to have to understand how this norm deviates from the true L2 norm, and actually how it deviates from this norm for functions which are inside Vn. Let me explain that. So again, let's consider this random Gramian. It satisfies that the expectation is I. It's a symmetric matrix. And if you consider any vector of this form, described by these coordinates, you see that this norm is just the quadratic form associated to G applied to this to the coordinates of V in Vn. On the other hand, the quadratic form associated to V to the true norm V square is just the identity. Okay? When you represent a vector in Vn in the orthonormal basis. So what does it mean? It means that if you want to understand how equivalent do you have this kind of norm equivalence for all V in Vn, this is just equivalent to saying that G deviates from the identity by the amount here. In that case, this is 1/2. I could have taken 1 plus delta here, 1 minus delta here. Okay? So this is now our question. And here, this is a spectral norm. So we are going to be interested in the deviation between this empirical Gramian and the identity. Okay? Why? Because suppose that this holds. Suppose that we have this norm equivalence uniformly on Vn. We cannot have this norm equivalence uniformly on every function, of course. Then what can we write? We look at the least square approximation and we look at the error, and we insert the true projection, Pn of u. Here I'm just using Pythagoras' theorem. I get the best approximation error. I get Pn of u minus un least square. And now I use this norm equivalence because this guy lives in Vn. So in the event where this holds, I can write something like that, you see? Where this is now the discrete norm. Okay? All right, so, but now I notice that, again, I'm using Pythagoras' theorem because I know that un least square minimizes the distance to u in the M norm. So I get this thing. Okay? And now I notice that the expectation of this norm, we remember that this norm is an unbiased estimator for the true L2 norm. The expectation of this is ENU square. So you have 3 times ENU square. This is a very crude little computation, but what does it mean? In fact, it means that if we want to be completely careful, we need also to account for the event where we don't have this concentration property. So if we don't have this concentration property, you know, if we deviate from the identity bigger than 1/2, we can measure that. We can look at the Gramian matrix and see if this happens. In that case, well, we don't trust the least square solution. We say this is not stable. So better set it to 0. So in that case, you see what is actually the true error estimate that you retrieve. You see that with this precaution, you have at u minus un d square in expectation is bounded by 3 times En of u square, but you have to take into account the probability that g minus I is bigger than 1/2. And this gets, and because in this event I took 0, so I have u square. Okay? So I have instance optimality up to this probability of failure. And this is what I have to analyze now. All right. So here we go. And there's going to be a key ingredient to our analysis. Let me say what it is. What is this? Sorry. So the key ingredient will be the following. Remember, L1, Ln is an orthonormal basis of Vn for this norm. And we are going to introduce this function. So we take the sum of the square of these functions. We multiply by the weight. I call this KNW. And we take the L infinity norm, KNW, capital KNW. So this is a soup over the domain where y lives. Okay? So let me give the remark that these quantities are actually independent on the choice of the orthonormal basis, because if you make a change of basis, it just make a rotation, this sum of the square is not going to change, right? So they do not really depend on the orthonormal basis. They depend on Vn, on the measure rho on W. Okay? Oh, sorry, I just don't want this to happen. I need this to check the time. Okay. Airplane mode. That's done. Time is, okay. Yeah, we have time. Okay. What is this? Oh, you know what this is? This is Ingrid Dubichy receiving the L'Oreal Prize. Do you see her? That's Ingrid. That was last week. Huh? This is stupid. This is when I plug my telephone. This has to do with my telephone. Sorry. There's a big thing called Women in Science, maybe. And Ingrid Dubichy received it at UNESCO. All right. Okay, back to this. So what can we say about this quantity? This quantity, you see, first of all, let's notice what happens when you integrate this function. When you integrate this function with respect to d sigma, with respect to the sampling measure, Well, remember integral d sigma multiplied by w is 0. So you integrate with respect to d sigma because this is an orthonormal basis. Everyone integrates to 1. And so this integral is n. So since the average is n, the sup norm is certainly bigger than n. Okay? That's essentially n is the smallest value you could hope. You would need that the average is equal to the sup norm, so you would need something which is flat, in fact. Okay? Constant. So in the unweighted case, what do you have? You have actually something which is familiar to people in approximation theory. W equal 1, you get this thing. I just call it Kn of y. This is called the inverse Christoffel function. It has lots of interesting properties, very highly studied in the case of polynomials, for example. So if you think about what it is actually the diagonal of the integral kernel associated to the orthogonal projection onto Vn. And it's also the best constant for the inverse estimate when you want to control the L infinity norm by the L2 norm. Okay, the L2 norm is obviously bounded by the L infinity norm with constant 1. You would like to have the other way around. For all functions in Vn, you would like something like some to bound the L infinity norm by L2. Use Cauchy-Schwarz, and you see that the best constant is going to be given by this, the max of this inverse Christoffel function. So there's all kind of interesting property with this, and I will talk about it. But more generally speaking, this is what we have. And now you remember what I want is to have some probabilistic control on this thing. And here is the probabilistic control. So this is the theorem. And it was given in slightly different form and only in the polynomial context by Duston and Hampton. So I really have to give credit to them. We rediscovered this in a sort of more general framework. And the theorem says the following. If you want that this probability is less than epsilon, a sufficient condition for that is that this quantity Knw that I defined in the previous slides is bounded by m divided by log of 2n divided by epsilon. Okay? So, what does it mean? And C here is just this constant. Okay? So that means if you have this, again, if you have set to 0 when G is deviate too far from the identity, you get this instance optimality bound up to this probability of failure, and you get it under this condition. This is a kind of stability regime that tells you when things are going well. Okay? So, imagine that En decays like a certain algebraic power, like n to minus s. Then you might as well, one way to not to be bothered by this term is to say we're going to take epsilon to be like n to the minus r, where r goes faster than the decay rate of En squared. Okay, when this decay rate. So you want not to be bothered by this term. So you see that you enter some additional power of n here, but these are essentially log factors. Okay? So the condition becomes like Knw is bigger than m divided by log n. Okay? So now we want to think what does it mean in terms of a sampling budget. You have a sampling condition that m should be up to constant bigger than Knw multiplied by log of n. And we say that Knw, if you remember the previous slide, Knw is larger than n. So that's your sufficient condition. That's the condition you need. But of course, it could be problematic if KNW is much larger than n. Okay, so now we have this regime. If KNW is equal to n, if it's minimal, then you have a rather good, you are in good shape. If KNW is n square or exponential n or something else, then the regime becomes quite demanding. And I want to give you evidence that this condition is sort of sharp. Oh, do I have time for this? Yeah. Okay. I think this would deserve more time to explain where this theorem comes from. So before I give an idea of the proof of this, I want to illustrate. And I want to illustrate in the case of in the unweighted case. So in the unweighted case, the stability regime is described by this condition. Okay, because KNW becomes KN. So your stability condition is that the number of samples up to log n should be bigger than Kn. Now, we can estimate this inverse Christoffel function in all kind of cases of interest. And let me give a very simple case, which are the univariate polynomials. Okay? Let me give two examples. Think of rho to be the Chebyshev measure. So this measure is such that the Lj are the Chebyshev polynomials. So the Chebyshev polynomials are very flat. They are cosine, cosine function, cosine of n times r cosine x, right? So it means that these Lj are essentially, each of them is like 1, and Kn is essentially behaving like n. Okay, so the stability regime up to log factor is quite generous. You just have that m should be bigger than n. Now take the uniform distribution. Then these Lj are the normalized Legendre polynomials. Okay? The Legendre polynomials, they are not completely flat. Huh? They grow a little bit on the boundary. And in that case, Kn, you can show that this is n squared. So your stability regime will be that you need to invest n squared sample. And this is confirmed numerically. Let's check it. You see here I'm just looking at, in order to check the deviation from the identity, I check the condition number of G. Because if it's between 1/2 and 3/2, its condition number should be less than 3. And so we sample and we empirically compute the probability that this happened, that you are in the good regime. So here you have m log n, m divided by log m on the x-axis. So you have the number of samples, and on the y-axis you have the dimension n. Okay. And you see, this is exactly what you see. You are successful. Essentially, in the case of the Chebyshev measure, you are successful with a linear amount of sample. Here, it's a quadratic amount of sample. And on the right, I'm plotting something which is not covered by the theory. Take y equal r, and suppose that you have the Gaussian measure for rho. Okay, so this is just a Gaussian measure. In that case, the orthonormal polynomial are the Hermite polynomials. And so I would like to compute Kn. But Kn, because there is no weight, Kn is the maximum of the sum of the Hermite polynomial over all R. So polynomials are unbounded. Okay, so Kn is infinity. So the theory I gave does not cover this case. You can try to find something ad hoc to understand when there is stability, and you actually find something. By the hand, you find that stability holds, but with an amount of sample which is extremely prohibitive. It's actually exponential in the dimension. And actually, this is what you see if you look very carefully. You have a little regime here where you are stable, but it's absolutely prohibitive. Okay? So you cannot, that shows you that sampling according to the natural density can be good sometimes, but in general, it's going to be problematic for what you want to do. And this is where a better sampling will be needed. Okay? So this is why the unweighted case is not so good. Okay, so I think it's a good time to take a break. I return to this theorem. I will give a little explanation after the break, and then go to the right sampling strategy.